Hi everybody. So the next section, 8.2, is about exponential functions. So one thing I want to mention is we are going to use the stuff we used in 8.1, but in more general form. So remember 8.1 we talked about inverse functions and things like that. And so what we're going to look at is a specific set of functions and their inverses. So 8.2 will be sort of a more specialized version of 8.1. So what we'll look at is we'll define what an exponential function is. And basically, I think I talked about this in the last section, right? An exponential function is something where you have the variable in the exponent, not the base. And then we'll take a look at this number e, which is related to exponential functions. And then we'll solve some simple exponential equations, and then we'll look at applications of exponential functions and where we can use them and things like that. So like I said, an exponential function then is just something of the form y equals some number raised to some power. And you can have variations on that, but one thing is b has to be greater than 0 because it doesn't really make sense to take powers of a negative number. And then also b can't be 1 because if it is, you just have the constant function y is equal to 1. Because 1 raised to any power is also 1. So some examples would be like something like, say, 2 to the x or 3 to the x. You can also multiply the b by a number. So like, for example, your b might be 5. You could multiply that by 3, and then the power you could write as 2x. And I suppose you could rewrite this as like 3 times 25 to the x, right? Because 5 to the 2x is the same thing as 5x squared. But the thing to note here is that the x only applies to the 25 or the 5, not the 3. Or you can have, again, b can be between 0 and 1. It just can't be negative, so you could have something like that. So these would all be examples of exponential functions. So one question you might have is, okay, well, what do these exponential functions look like? Well, let's graph one. Let's graph y is equal to 2 to the x. So if you just plot points, right, pick values and stick them in for x. So if you stick -2 in for x, you'll get 1 over 2 to the second power, right? Because remember, if you have negative exponents, that's the same thing as 1 over that thing raised to the positive power. So that'll give you 1/4 for the y-coordinate. If you put in -1 for x, right, that'll be a half. Put 0 in for x, you'll get 1. 2 to the first power is 2, 2 to the second power is 4, etc. So if you plot the points and connect the dots, you'll see that you'll get a graph that looks something kind of like this. So one thing that exponential functions are used for then is to describe things that grow relatively quickly, like maybe population growth or something like that. And all the graphs will have the same basic shape no matter what the base is. If you have, the graph of 3 to the x, it'll probably grow a little bit more rapidly, but it would have the same basic shape, which would still go through the point 0, 1 and things like that. So one thing to notice about the exponential functions is the domain is the set of all real numbers, right? You can put any number that you want in for x, because no matter what you put in for x, you'll get a value for y. There are no x-intercepts, so it never touches the x-axis. So as you move out here, it'll get closer and closer to the x-axis, but it won't ever touch it. And then the graph contains the point 0, 1, no matter what the base a is. It also contains 1a, so in this case it contains the point 1, 2. And then it will also contain the point -1, 1 over a. So it'll contain the point -1, 1 over 2, which is given by that. But I think the most important thing to realize is that unless the graph is shifted left or right or up or down, it should always go through the point 0, 1, no matter what this base a is, whether it's 2 or 3, etc. So here's another example. So this is a little bit different. So if the number in here is greater than 1, right, the graph will go like that. But if the number in here is less than 1, it'll go like that. And again, you can plot points to see that's true. You could also think of this as 2 to the -1 to the x power, right? Because 1/2 is the same thing as 2 to the -x. So you could think of that as the graph of 2 to the -x, which would basically just be the graph of 2 to the x, which we just saw. This one just flipped around the y-axis, right? Because if you replace x with -x, I know we haven't really talked about that yet, but if you replace x with -x, that has the effect of flipping the graph that way. Or you can just plot points. So again, if a is between 0 and 1, right, again, you get the all real numbers as the domain, and the range is the set of all positive real numbers. You're never going to get 0. There are no x-intercepts. The y-intercept is 1, 0, and then again it will contain the same points. The thing is, though, is if a is between 0 and 1, the graph goes like that, and if a is greater than 1, it goes like that. And if a is equal to 1, you'll get a straight line, right, that goes through 1. And remember, a can't ever be negative, so we don't have to worry about that situation. So, so basically all exponential functions will look the same, right? But their shape will change a little bit depending on what the base is, right? So the triangles here, the graph of 3 to the x, e, which is this number we'll talk about later, which is about 2.7. That graph looks kind of like that. And then the little black diamonds there gives you the graph of 2 to the x. So again, you can see the shape is a little bit different, but they all kind of have the same basic shape, right? They start to kind of go like that. And then as I mentioned earlier, if the base is greater than 1, it'll go like that. And if the base is between 0 and 1, it'll go like that. I guess we already mentioned this, right? The graphs of the exponential functions have the same basic shape, right? They'll either go like that or like that. They all go through the point 0, 1, right? They always go through 1 on the y-axis. And the exponential functions are used to describe things that grow quickly. I guess in this case, if a is less than 1 or the base is less than 1, right, they might be used to describe things that decrease quickly. Now, as far as evaluating exponential functions, right, I mean, some of these you can just sort of do in your head. Like, let's say I asked you, what's 2 to the 5th? Well, that's just 2 times 2 times 2 times 2 times 2, right, which would be 2 times 2 is 4, times another 2 is 8, times another 2 is 16, times another 2 is 32. Right, this would just be 3 times 3 times 3, which would give you 27. Now, for something like this, again, e is really one of those numbers you can't write down exactly. We'll talk about that more later. We might have talked about that already, but if you forget what the number e is, most of the time there is a button on your calculator that will do that. So just type in e to the first. So like I said, e is about 2.7. You can think of it as being, a lot of people remember it as 2.71828. So it depends on how many, places you round that to. But e is kind of like the number pi. You can't ever write it down, and it may look like there's a repeating pattern here with the 1828, 1828, but that actually doesn't repeat after that point. But if you take that number and raise it to the 7th power on your calculator, right, in that case that would give you about 1096.633, something like that. And again, something like that, I would certainly not expect you to do that without your calculator. Or this one, again, I might expect you to do something like this without your calculator. You can think of that as 1 over 5 squared, which would be 1 over 25. And again, if I had you do that without a calculator, you could just leave it like that. I guess you could also write it as a decimal also. So it depends on the instructions, I guess, for those. But, make sure that you know how to evaluate exponents without your, with and without your calculator if you need to. Right? If I want you to calculate 2 to the, to the 11th power, right? You could probably do that without a calculator, but so a lot of times it's quicker to do that without a calculator. So that brings us to this number e that I was talking about, and it turns out that the number e you can think of as the limit of this function as n approaches infinity. So as you let n get bigger and bigger, it'll get closer and closer to this number e. So like, for example, if you let n be equal to 1, that'll give you 2 to the first power, which will be 2, right? If you let n be equal to 2, that'll be 1 plus 1/2 to the second power, so that'll be about 1.5 squared, which if you take 1.5 squared, I think that's, what, 2.25? So you can see that you get a little bit closer to e. If you let n be equal to 3, for example, that'll be 1 plus 1/3 to the third power, so that'll be 1.333 repeating to the third power. So if I just take that and put that into my calculator here and raise that to the third power, I get about 2.37037, which is again even closer to e. So as you keep increasing that number, And again, you can't ever let n be equal to infinity, but as you make it bigger and bigger, it will get closer to that number e. And this is sometimes called Euler's constant because it's named after the mathematician Euler. Or if you have like e to the x, it may be referred to as the exponential function or natural exponential function. So I don't know if it's named e after Euler or e after exponential, but just remember that e is about 2.7, just like pi is about 3.14. So as I mentioned, right, for this formula, as you let n approach infinity, this will get closer and closer to the e, right, which again is about 2.71828. And we'll see some applications of this maybe later on. I don't know if there's anything that's like really important that you know for now, but we'll maybe look at some applications later. So the next thing I want to look at is solving some simple equations with exponents in them, which we haven't really done yet. And we'll see that we'll do some more complicated versions of this later on in one of the later sections. But basically, if you have two things that are equal to each other, if the bases are the same, then if you think about it, the exponents have to be equal, right? If I have like 2 to the x is equal to 2 to the 5th, well, what does x have to be? Well, x has to be 5 if they're equal, right? So in terms of solving exponential equations like this where you have the same base, and we'll look at different bases later on, you basically use the laws of exponents to write both sides of the equation with the same base, and then you just set the exponents equal to each other, and then solve the equation. And then you really shouldn't have to check your answers for these. Again, assuming that you haven't made an arithmetic mistake, the answer that you get should be the answer, but it's always a good idea to check just to be on the safe side. So let's say you wanted to solve this equation, right? You're basically asking what power would you raise 2 to get 1 over 64? And you might be able to do this without any algebra just by thinking about it here. But if you think about it, 64 is the same thing as 2 to the 6th. So rewriting this side, you can rewrite 1 over 64 as 2 to the negative 6. Well, if the bases are the same and they're equal, that implies that x has to be negative 6. So that would be your answer, right? And then, again, good idea to check. If you check it, it does check out. Okay. So here's some other examples. Let's say you wanted to solve this equation. Well, again, the base is already the same, so you don't really have to do a whole lot there, right? That'd be 5x minus 3 is equal to x plus 5. So go ahead and move everything with x over to one side and everything without x to the other side. That will give you x is equal to 2, right? And if you check that, that will work out. Just won't bother checking that one in this case. Now for this one, you want to rewrite the 9 as 3 squared. So that'll be 3 squared to the x is equal to 3 to the x plus 3. Once you've written it that way, you can write that as 3 squared x, because remember, when you raise a power to a power, you multiply. And now the bases are the same, so just set the exponents equal to each other and solve. Right? So if I'll just subtract x from both sides, I get x is equal to 3, and that should work out, right? 9 to the 3rd power is the same thing as 3 to the 6th power. Here's an example of an application here. So there's something called Newton's law of cooling, which is an equation that describes how the temperature of something decreases over time. And the equation in this case is given by this following formula, right, where this is the room temperature. This number here is the difference between the initial temperature and the room temperature, and then this depends on the object that's cooling down. So this number here will change depending on what object it is that's cooling down. Like if it's metal instead of a pizza, this might cool down faster or something like that. But what we're asking here then is, so this equation basically gives you the temperature of the pizza at time t after you've taken it out of the oven. So the question is, what will be the temperature of the pizza after 10 minutes? Well, all you have to do then is just put 10 into the equation, assuming that this t is supposed to be in minutes, and then simplify that, right? So, so here, maybe just to clarify this a little bit, if you take E and you raise that to the negative, make sure you use that button, not the subtract button there, 0. Well, I guess we're moving the decimal over anyway, multiplying by 10, right? So if you take that, right, that gives you about, this number here will be about 0.48652. Oh, sorry, I forgot a 7 in there. But if you take that number times 330, that number there will be about 160.628. So take that and add 170, and that'll give you about, so after 10 minutes, right, the pizza will have cooled to about 230 degrees. Right? So you could maybe see where you could maybe use that in an industrial process, like maybe you're heating some metal and you want to figure out, you know, what the temperature is going to be after 10 minutes or 20 minutes, so you can start working with the metal so it doesn't cool down too much, so it's still malleable, right? That would be an example of where you could use Newton's law of cooling. Another example where you can use an exponential function is compound interest. So the amount of money you'll have if you invest an amount P called the principal at annual interest rate R for T years is given by the following equation. Where again you're compounding n times per year. So if you're compounding once a month, n would be 12. If you're compounding once per quarter, right, n would be 4. Right, once a week, n would be 52, etc. So, so let's say that you deposit $3,000 into a Roth IRA, and you want to determine the future value of the deposit if it earns a constant interest rate of 8% interest compounded quarterly. So that would mean that n is equal to 4 after 35 years, right? So plug that information into the equation and work it out, see what you get. So plug 3,000 in there, write this as a decimal, so that would be 0.08 for R, and then n would be 4, and then plug in 35 for T, right? So go ahead and plug that into the formula, and then just work it out, right? So here you got to take 1.02 raised to the 140th power. So when you're doing this, make sure you multiply this out first, and then raise it to that power, because if you accidentally raise this to the 4 times 35 power and you don't have that in parentheses, it's going to take this thing raised to that power times 35, which is not what you want. So either put this in parentheses or work this out first. And so basically after 35 years, your initial investment of $3,000, assuming it pays a constant interest rate of 8% interest, will have grown to about $48,000. And the important thing to realize is this is an exponential function, at least if you let t or n vary, right, if you consider those to be your variables. Here's another example. Let's say that the population of a town in 1900 was 50,000. If the population doubles once every 15 years, find the projected population in the year 2100, right? And this model assumes certain things, like, I mean, so there's no guarantee that the population of a town is going to constantly double every 15 years. Maybe that's an average. And so assuming that that trend continues, what would the estimated population be? And maybe you're trying to do that. Maybe you're an urban planner and you need to figure out how much money you need to budget for extra roads or sewer pipes or something, and so you're trying to get an estimate. So in this case, you'd start out with 50,000, right, and then it doubles every 15 years. So basically take 2 raised to the t divided by 15, and then I guess if you think about it, right, 2,100 would be about 200 years after t, so that would be about 50,000 times 2 to the 200 divided by 15. Right, so you want to figure out how many 15-year periods there are in that 200-year interval. So take, oops, sorry, I guess I want to divide by 15, not 12, right? Take 200 divided by 15 will give you about 13.33. So take 2 and raise it to that power. I'm just going to use the answer button to get that. And then take that number times the 50,000, right? So that initial small town, which, you know, like 100 years ago was $50,000, 100 was 50,000 people, right? Will be about will be really big if the rate doubles there, right? So in about 100 more years, right, it'll be about 500 million people. Okay, so there's another example of an exponential function where, again, t is the thing that's allowed to change. Here's another compound interest formula. I guess we already kind of talked about that. One thing I did want to mention here also is for this formula, this assumes that n is finite, that the number of compounding periods is finite. You might wonder, well, what happens if n is infinite? Like, what if you could compound every possible moment in time that you can? I guess that's sort of impossible in practice, but like, let's say you compound not every minute, not every second, but even more often than that. Well, if you look at this equation, this might look, if I take out the r and the p and the t, this might look like something we've seen before, right? So what we're basically kind of asking here is take the limit as n approaches infinity. In other words, as n gets larger and larger, what does this get closer to? Well, remember, we kind of looked at this earlier. Remember, that was equal to e. So it turns out that if n is actually infinity, this equation here will change to this equation, right? And again, the reason why is because of that formula. So let's say, for example, we want to find the amount of money invested or accumulated at the end of 60 years at 2.5% interest if you start out with $1,000. So let's say we're doing this annually. So remember, the general formula here is A is equal to P times 1 plus R over n to the nt, at least if n is finite. And then if we're doing this continuously, if n is infinite, right, we would use this equation. So this would be if n is less than infinity, and this would be if n is equal to infinity. So annually would just be once per year. So in that case, n would be 1. So the amount that you would have after 60 years, if you only calculated the interest once per year, would be the initial amount of $1,000 times 1 plus, writing this as a decimal, or as a decimal, right, would give you 0.025 over n, which is just 1, to the 1 times t, which is 60. Right? So how much will your money grown to after 60 years if you put in $1,000 and it just compounds once per year, right? So if you work that out, right, that would be 1,000 times 1.025 to the 60th power. So again, you can see where we're using exponents again, right? So take 1.025, raise that to the 60th power, right? That gives you about 4.3997, something like that. And then just take that times 1,000, which is just going to move the decimal over 3 places. So that'll give you about $4,399.79 if you round to the nearest penny, right? So you just stick $1,000 in the bank 60 years later, right? And maybe you start the account when you're 10, right? When you're 70, you'll have that much money in the bank. So not a whole lot, right? This assumes that you're not putting in a certain amount per month. You're just putting in a one-time amount. Now for quarterly, n would be equal to 4. So in that case, A in this case would just be 1,000 times 1 plus 0.025 divided by 4 times 4 to the 60th power, right, which would be 240. So here you should see that you'll have a little bit more interest because you're compounding more often. So if I take 1 plus 0.025 divided by 4, that gives me a value here of about 1,000 times 1.00625. That's going to be raised to the 240th power. So if I raise that to the 240th power, I'll get 1,000 times 4.460817 roughly. So if I multiply that by 1,000, right, I'll have 4,460.82. Right? So you can see if I compound 4 times a year instead of once a year, I wind up with a little bit more money, right, about 61 extra dollars, something like that. So if I do this monthly, I would do the same thing, except in this case, n would be equal to 12. So that'd just be 1,000 times 1 plus 0.025 divided by 12 raised to the 12 times 60 power. Right? So I'm just going to throw this whole thing into my calculator. So I'll take 1,000 times 1 plus 0.025 divided by 12, and then just be careful when you're doing this. When you do this, make sure you put the 12 times 60 in parentheses, otherwise it'll raise it to the 12th power and then multiply your result by 60, which is not what you right? So if I work that out, that gives me about 4474.70, right? So in that case, I get maybe an extra $14 over the 60-year period, so not a whole lot. But let's say I want to do this daily then, right? So in that case, I would have the same equation, except n would be 365, right? So if I just go up and edit this equation here, if I can, maybe I can't. Let me type it in again here. So if I put in 1,000 times 1 plus 0.025 divided by 365, we'll assume there are 365 days in a year. I know there's really 365 and 1/4, but and then again raise that to the, again in parentheses, 365 times 60 years, right? So if you were able to compound daily, right, again you'd make a little bit more money, right? In that case, you'd make $4,481 as opposed to $4,474.70. So again, you only make like what, an extra $9 or $7, I guess, roughly. So you can see that as the compounding period goes up, or the number of compounding periods goes up, right, the dollar amount goes up, but it kind of shrinks every time. So you might wonder, well, what happened if you did compound continuously, right? What if you let n be equal to infinity? Remember, in that case, we have to use the equation a is equal to p to the ERT. So you might wonder, well, do you have an infinite amount of money or a finite amount of money? Well, let's find out. So it'd be 1,000 times, sorry, not plus, times e. So I'm just going to use my e button. I guess you could put in 2.7. And then remember, r is 0.025, and again, you're taking that times 60. Again, just make sure you put that in parentheses. So you can see that if you were to compound every possible moment in time that you could, you still wouldn't wind up with an infinite amount of money, right? In fact, all you really wind up with is, what, about 20 cents more, right? Because you get $4,481.68. So again, I don't know if the banks actually do that, if they compound infinitely often, but if you can get your bank to compound more often, and keep the interest rate the same and the length of the term the same, right, you'll actually wind up with a little bit more money. Okay, so hopefully that should give you guys an idea of what to do with that section. So if you guys have questions about that or anything, just let me know.